10 a.m. Let's continue. So, in the previous classes, we introduced one of the fundamental laws in physics, Faraday's law, right, which explains this. Let's just quickly review. So, if you have a conducting loop exposed to the external magnetic field, of course, as a result, there will be magnetic flux produced by this magnetic field. So there is a loop, there is a magnetic field, there must be magnetic flux. If that flux changes in time, if d phi over dt is not zero, then EMF, potential difference, will be somehow produced in this loop. If there is an EMF, as a consequence, of course, there will be current, induced current. So we call it induced EMF and induced current, right? Of course, expression for the flux, it's a B dot A for the simplest situation, which we usually have: uniform magnetic field, flat area. That's what we usually have, right? Then minus in front of this expression takes care of a direction of the current, clockwise or counterclockwise in the loop, right? And Lenz came up with the rule which can be used to find that direction. So let's quickly review that. So if flux flowing through the loop, or if flux, magnetic flux through the loop increasing, if flux increasing, then the whole idea is that the loop doesn't like when flux changes, right? The loop wants to see the flux as constant as it's possible, right? So if flux increases, a loop doesn't like it, and in this case it rebels. It tries to suppress the growing flux. In which way? It starts driving current in such a direction, so the induced magnetic field will be in the opposite direction to the direction of the external magnetic field. Now, once you know the direction of the induced magnetic field, you apply right-hand rule, opposite directions, then you apply right-hand rule number 2 in order to find the correct direction of the induced current, right? So in this case, if magnetic field is in, so I have to apply position my fingers like this, and my thumb gives me the correct direction. So that's the first situation. Now the second, what if magnetic flux is dying? So now the response of the system completely different. It becomes supported because it doesn't like when flux changes. Flux is dying, it tries to support it, tries to keep it as constant as possible. So in this case, it drives the current, induced current, in such a direction, so the induced magnetic field will be in the same direction as the external magnetic field, right? And then of course, we again can apply, once you know direction of the induced magnetic field, a right-hand rule, and you can get direction of the induced current. So that's how it works. And we already, in this section, we looked at the example, and we also looked at the problem 14, part A. So now you're familiar with the whole game. Now today we're going to look at some situations which are slightly different, and of which you must be aware, right? So let's continue with problem 14, and now I will skip part B. In your homework, you'll have to do, of course, the whole thing, part A, B, and C. We solved part A, part B I will skip, and now let's look at part C. So I separated this, so it's a 14, part C. Right. Okay, so what do we have here? External magnetic field. Okay, let me draw it here. Like this. Again, you see it's uniform. At least I'm trying to draw uniform magnetic field lines, right? So density of lines, the same. And in part A, which we solved in the previous recitation class, the loop was positioned like this, right? Perpendicular to the magnetic field lines. But what if and in part B also will be similar situation, right? But what if in part C we turn the loop like this by 90 degrees? Right? So what can we tell about induced current in this situation? Right. Okay, let me draw it. This situation. Okay, the loop will be, so let me just draw two circles, and lines connect. Oop, what an ugly line. Okay, on the screen looks better, but since it's in front of me, it is ugly. Still ugly. Okay, good enough. So that's my loop. Okay, and again, we will have to, of course, we have loop exposed to the magnetic field. So it looks like we can apply Faraday's law in order to answer the question what happens to this loop in terms of production of the induced current. Okay, so, and again, as usual, we need to figure out what happens to the flux, because it's all about flux. And that's why in physics even special SI unit was given to flux, because every time in this Faraday's law you analyze flux, right, in order to make people's life easier. So special unit was given. Okay, so let's start. Again, the final result, of course, we need to find out what happens to the induced current. But as a preliminary, of course, we need to understand what happens to the magnetic flux. First, can you answer conceptually, kind of quickly, without any calculations, what will be the value of the flux, magnetic flux? Most of you should be able to see that immediately. If you still don't see it, remember, what's the physical meaning of the magnetic flux? In simple words, it's just basically number of magnetic field lines crossing a surface, right? So if you have magnetic field lines, surface, right, and then basically it's a number which allows us to calculate number of magnetic field lines crossing this surface. In this situation, magnetic field is this way, is parallel to the surface of the loop, right? Is parallel to the surface of the loop. So magnetic field lines physically cannot cross this loop. They are parallel to the surface. So physically cannot cross. So what should be the value of the magnetic flux? 0. The value of the magnetic flux should be 0 in this. Not should be, is 0. Right? You see that? So that's conceptually. Conceptual explanation of why magnetic flux is 0. But now let's actually show it mathematically. Let's show mathematically. So from the definition, so magnetic flux, it's a dot product between B and A, right? And of course, if you write it explicitly, okay, it's a B external. B external times area times cosine of angle. Of course, let's draw area vector on the picture. You remember area vector must be perpendicular to the surface. So it means that it can be this way, perpendicular, yes, or this way, perpendicular, yes, right? So you have freedom. You can pick this way, you orient it this way or that way, right? Okay, let me orient it in this direction. I use my freedom this way. Wait, it's A. It's A. All right. Okay, and now what's the angle between magnetic field, which is into the board, and area vector, which is that way? So A, B, B, A. So the angle between them is 90 degrees, right? So that's the situation. So angle 90 degrees, cosine of 90 degrees is 0. That's the mathematical explanation of why flux is 0. 90 degrees, this is 0, and the whole thing is 0. So flux doesn't change. It's not a crime that the flux is 0, right? But in this case, that 0 stays 0 in time. It doesn't change as time goes by. It stays constant. If flux is constant, the loop will be completely happy in this case, and it is not going to produce EMF, and it is not going to produce any induced current. So in this case, induced current will be 0. So EMF equals to minus d phi over dt. So it will be also 0, and as a result, induced current, which is EMF over the resistance, will be also 0. So But again, conceptual explanation that because magnetic field lines don't cross our loop. Okay. Again, if something not clear, tell me. Right, I will explain deeper. Although I think I trying to be as thorough as possible. So next problem, 13. And you know what? I'll probably go to that side of the board. So the whole problem will be on one side of on one part of the board. So problem 13. Now we have this situation. Let's say up to this line, there is a magnetic field above this line, uniform magnetic field, and magnetic field below this line is 0. Okay, and direction, let me check. Dots, bunch of dots. So this. So that's our B external. And below this line, B external equals to 0. Okay, information about the magnetic field and also the value of the magnetic field is given 0.2 Tesla. So B external equals to 0.2 Tesla. Then there is a now rectangular loop. Here we had a circular loop, now a rectangular loop. All right, let's see. Let's say it's like this. Okay, rectangular loop of width L. L is also given. So then, okay, let me write. So we have conducting loop in parameters. L equals to 5 centimeters. Okay, 5 centimeters. Of course, at some point you will have to convert to meters. I usually do it immediately. Then, what else? Resistance. Resistance of this loop is, actually, what's the value? 0.1. 0.1 ohms. But that's not the whole story. Now, this loop is being dragged down. Okay, assume that there's no magnetic, there's no gravitational field, just only electromagnetic part in the loop. Right. So this loop is being dragged this way with velocity v. The value of v is given. V is 50 meters per second. Okay, guys, it's problem 13, but I changed one parameter. In problem 13, V is up. The loop is being dragged into the magnetic field. But here, I decided to solve the problem when the loop is pulled out of the magnetic field. But again, in your homework, will be a reverse situation. So idea, philosophy will be exactly the same, but of course you will have to adjust properly all the directions and so on, right, for that situation. Okay? And the same question. So we need to answer the question about the induced current, the value of the current and the direction of the current. Okay, let me check if I mentioned, if I gave you everything. Yeah. Yep. So we need to find I induced loop, conducting loop, exposed to the magnetic field. It means that we need to apply Faraday's law, right? In terms of physics, right, it's a direct application of the Faraday's law, right? But of course, carefully, right? And Faraday's law, 2 steps: direction, the value. Let me start with the direction. I usually like to handle first the direction because it's kind of semi-conceptual, right? And then at the end, I can crunch some numbers. Right, so let me put the first bullet, direction. Again, we need to start with the flux, because in the length rule, we need to figure out what happens to the flux in order to continue. Right? So inside of the flux, again, three parameters, B, A, and the angle between these two vectors. Right? So B external, area, and the angle between them. So let's analyze all of these parameters. B external, what can you say about the value of B external? 0.2 Tesla. It's constant, right? So magnetic field doesn't change. So B external is constant. Then angle. I skip area. I will talk about the last, right? Angle, again, it's up to you, right? So again, you can align your area vector out of the board or into the board. It's up to you. But you remember I told you that I usually prefer to choose the direction of A in the same direction as the direction of the external magnetic field to make that angle 0 all the time. Yeah. Okay, so B is out, so my area will be also out. Area vector. This is my A, right? You see dot, green dot, means out. So in that case, angle is 0 because we have two parallel vectors. But anyway, it's constant. It doesn't make our flux change. It doesn't change our flux. Right? So now area. Okay, that's one of the most important part of this problem. Because in the problem here, 14a, in the previous class which we solved, right? You remember we had area, and area was area of the loop exposed to the magnetic field. We had this situation, right? And we did not change the area of the loop, right? And the whole loop was exposed to the external magnetic field. Here, again, the total area of the loop stays the same. We do not change the area of the loop, right? The total loop. But we are talking about the magnetic flux, right? And this part of the loop, which is not exposed to the magnetic field, is not going to contribute anything to the flux, right? So, like here in part A, the whole loop was exposed to the magnetic field, and as a result, the whole area of the loop contributed to the value of the magnetic flux. Now, this part of the loop does not contribute anything. Flux through this part of the loop is 0. Only this part of the loop is exposed to the magnetic field, and only this part of the loop is going to give us a non-zero magnetic flux. So that's the major difference. Although area of the loop total area of the loop stays the constant, but this area which is exposed to the magnetic field, and we need to use only that area in our analysis of the magnetic flux. Okay, let me highlight this area. Right. Okay, so which way I wrote it? So area only exposed to be external. Again, no magnetic field, magnetic flux is 0 through this part of the loop. This part, yeah, exposed to the magnetic field, and of course, that will give us magnetic flux, right? And what happens to this shaded area as we drag this loop out of the magnetic field? It's getting smaller and smaller and smaller and smaller and smaller and smaller, right? And of course, eventually this loop will be completely out of the magnetic field. But we only discuss that part, that stretch of time when the loop is exposed to the magnetic field, right? Okay, so, and yeah, as I said, this part of the loop is the area is decreasing. Okay, so now as a result, and that's the major difference between the previous examples and this example. Again, in the previous example, the whole loop was exposed to the magnetic field, and the whole area of the loop contributed to the total flux. Here, although area of the loop physically stays the same, but we need only this part which is exposed to the magnetic field. So not the total area of the loop contribute to the total flux. Again, that's the major difference between this and previous examples. So as a result, I can come up with a conclusion what happens to the magnetic flux. Area is going down, so the flux is going down, decreasing, right? So now we have to use this part of the Lenz rule. A flux is dying, so the system becomes supportive, trying to support dying flux. So it means that B induced magnetic field will be in the same direction as B external. Okay, in the same direction, it means that I need to draw a bunch of red dots. Right. Okay, let me draw a few and stop for a moment. So that will be my B induced. And stop for this, I stopped for this reason. Okay, where should I draw these red dots? Should I draw them only in this part of the loop? Or should I draw them everywhere inside of the loop? Again, during the normal semesters, I usually try to get all these questions out of students, right? But now it's more complicated, so I'm trying to play both parts, right? All right. Most of the time, students' response is this. They tell me, okay, of course, we need to draw only in this upper part of the loop. But when I ask, so what's the source of this induced magnetic field? Of course, everyone knows the source of the induced magnetic field is the induced current flowing through the whole loop. Induced current flows everywhere in the loop, not just in the upper part of the loop. If the induced current flows everywhere, of course it flows also here, right? If there is a current over there, of course that current produces magnetic field, induced magnetic field, even in this part of the loop, lower part of the loop. Again, it's not big a deal. You can solve the problem without realizing that. But since we're discussing physics, why not to emphasize on this also interesting part, right? Since induced current flows everywhere, of course, this induced magnetic field will be everywhere. External magnetic field, again, it's only limited up to this line. But induced magnetic field, of course, will be everywhere. Okay, so it means that I can continue drawing these dots and even over here. Right. Okay. So now the last step. We need to apply right-hand rule in order to find the direction of the induced current, right? So I induced, what's the direction? Where is my loop? So induced magnetic field is out of the board, right? Dots out of the board. So it means that I have to position my fingers like this. All right. So now my fingers within the loop out of the loop. Or if you position it here, it's still the same, right? Here, still the same, right? Because if I position this way, no, it's wrong. This is correct. So my thumb gives me correct direction, which is counterclockwise. So that's CCW, right? Again, it is done using right-hand rule number 2. So first part done, direction. Now our magnitude. Okay, so absolute value of EMF. So EMF equals to minus absolute value of minus rate of change of the magnetic flux. And let's just, okay, minus can be dropped. Absolute value will take care of that. And explicit expression for the magnetic flux, BA times cosine of angle. Again, it's a B external times A and times cosine. Which angle? We already discussed. I already made a decision about direction of A. So it's out of the board in the same direction as B external. So it means that cosine of 0 degrees. Cosine of 0 degrees is just 1. Okay, so let me write it down without this cosine. D over dt, B external times A. So now, which quantity is constant in time out of these two, if there are any, right? B external, it's constant. What about area? Again, area exposed to the magnetic field. This area is not constant. As we drag this loop down, what happens to this area? It's getting smaller and smaller and smaller and smaller and smaller and smaller, right? Okay, let me emphasize that A, it's okay, maybe I will write this way. Again, exposed to be external. Exposed to be external, right? So B is constant, so we can take it outside of the sign of differentiation. And actually, we can take it outside of the sign of an absolute value because that is just a magnitude. Magnitude of the vector cannot be negative, so we can take it outside of the sign of absolute value, right? So now let me write, so B external equals to constant, so we can extract it. So it will be B external times absolute value of dA over dt. And again, A is exposed to a magnetic field. Okay, so now we have to use the same trick which I used in the lecture. You remember we had U-shaped rail, there was a rod, right? And that rod was moved to the right, right? And you remember what was the trick in order to connect what? Connect what? This is areal velocity, how fast area changes in time. We can say it's areal velocity, right? We need to connect this velocity, areal velocity, with this linear velocity, right? And in order to make this connection smooth, it makes sense to introduce, again, temporary, just for a couple of minutes, this distance. Let's use it x. Let's call it x. And the same trick I used in the lecture. Okay, so now let me introduce this x, right? And now let me write it down over here. So I will open my explanation box, and it's a, let me write introduce x for a couple of minutes. And then, so how can we write this area? Again, area exposed to the magnetic field. Width is known, length is x. So it's a rectangle, L times x. So area equals to L times x. Okay, so we can plug it. So it will be B external and d over dt, L times x. L is constant given. Of course, x is not constant. No way. X is getting smaller and smaller and smaller, right? But L is constant, the width of the loop. So L can be extracted also. So it will be B external times L and times dx over dt. And what is dx over dt? I remember sometimes students didn't see immediately Now, how fast this x changes in time? It's v, it's speed, right? So it is equal to b external times L times v, right? Of course, this dx over dt, it's negative because x is getting smaller and smaller and smaller and smaller. But we have the sign of an absolute value. So we just need to know only the magnitude of EMF. Okay, so B is given, L is given, V is given, so plug, and you will end up with EMF equals to 0.5 units. It's just EMF, potential difference, right? Of course, the nature of this EMF is different, right? But still, potential difference. 0.5 volts. Okay, and now, of course, what's the value of the induced current? If there is an EMF, it's a conducting loop. Ohm's law works, right, for metals. So current will be EMF divided by the resistance, which is also given. So now, final step, I induced equals to EMF divided by R. 0.5 ohms divided by 0.1 volts divided by 0.1 ohms, right? So 5 amps of current. Okay, so that's the problem. Again, the major difference between problems which we had before and now, although the total area of the loop stays the same, but in this case we don't need the total area of the loop, we need only that area of the loop which is exposed to the external magnetic field, which contributes to the magnetic flux. Okay, so that's why at some point I decided that we need to analyze this problem to emphasize on that particular part. Otherwise, the rest is very similar to what we had in the previous class. So what about time? Okay, awesome. We still have to look at enough time to look at more complicated situation. 46, problem 46. You know what, I can erase this 14C. So still chapter 30, problem 46. Okay, so the problem looks more complicated, but ideologically it's very similar to the previous situations, right? So what do we have in the previous case, which is just erased? And at the end of the previous class we discussed. So we had a loop and exposed to, it was completely exposed to the external magnetic field, right? It was the first situation. Now, over in this situation, we have a loop, but now it's partially exposed to the external magnetic field, right? This only upper part was exposed to the magnetic field. But what if we make this situation, again, the same loop, single loop, right? And only central part of the loop will be exposed to the magnetic field. How can we do that? We can take, for example, a solenoid. You remember what's the property of the solenoid? Inside of the solenoid, there is a uniform magnetic field. Outside of the solenoid, what's the value of the magnetic field outside of the solenoid? 0, right? You remember quiz number 5. And you even know the expression for the magnetic field inside of the solenoid, quiz number 5. So that's the example. If I take a situation, if I take the solenoid and position at the center of the loop, so only this central part of the loop will be exposed to the external magnetic field which is produced by the solenoid. The rest, this area, contribute nothing because there is no magnetic field flowing through this part of the loop, right? So what will be given? Of course, information about the loop, resistance of the loop, radius of the loop, right? And then information about the solenoid, length of the loop, number of loops, current. Information about the current through the loop will be given in terms of the graph, right? And of course, so since there is a flux, it looks like, right, through the loop, we will have to answer the question: what will be the value of the induced current in the loop and direction of that induced current, right? Again, so what's the difference? The whole loop was exposed to the magnetic field. Part of the loop was exposed to the magnetic field, and in this part, only this central part, small part of the loop, will be exposed to the external magnetic field produced by the solenoid. Okay, now let me give you a details. And of course, so what will be the approach? Again, the same steps. We need to find out what happens to the flux, right? So flux will be produced only by this central part of the loop. Expression for the magnetic field, quiz 5. Area of the loop, or area of the solenoid, information is given. So we will be able to find the expression for the flux. And then you take the flux, differentiate with respect to time, take all the constants outside of the sign of differentiation, and see what we're going to end up with. Okay, let's now get through these gory details step by step. And let me draw probably first the picture. Yeah, let me do it this way. So that's our solenoid. Right. Okay, maybe I can draw you this. Right. Solenoid. And then there is a conducting loop. Right. Maybe let me make it thicker. So that's our loop. Right. And some geometry is given. So this is radius of, okay, you know what? Let me write it on that side. That will be radius of the solenoid, r sub s small, you know what, let me make it a little bit bigger. S small. Yeah. Then radius of the loop is given. Radius of the loop, r sub L capital. Right. Right. So we have r sub s equals to, okay, let me grab my notes. What are the values? You know what, let me write solenoid and then write the parameters. So related to the solenoid. Solenoid. So r sub s equals to 1 centimeters. So it's a 0.01 meters. Then number of loops is given. Number of loops in the solenoid, 100 turns or loops, right? Length of the solenoid is given. So you see it's all related to the solenoid. Then length equals to 0.1 meters. So that's the information about the solenoid. And also we know how current changes in time. So let me probably draw it underneath. Right. Again, it's related to the solenoid. All right. Time in seconds, current in the solenoid. Then 1, 2, 3, 1, 2, 3 seconds. And current changes like this. So first it stays constant up to 1 second. Then it goes down to 2 seconds over here to the negative value. And then again it stays constant. This is minus 20 amps, units of amps. This is 20 amps. Of course, this point is 1.5, obviously, right? It should be 1.5 seconds. So again, that's how current changes in time. So let me write, I see the figure. Okay, so information about the solenoid, and now information about the loop. Information about the loop, R sub L is equal to 2 centimeters, 2 times 10 to the power of minus 2 meters. And resistance is given. Resistance is 0.1, I think 0.1, yeah, 0.1, okay, too big, 0.1 ohm. Yeah. So that's the situation. Of course, I can actually, in order to make it clearer, of course, let's assume that current is at a certain moment of time, maybe current is this way. No, current changes, right? You see, here current is positive. It means what? Current is positive. Actually, the problem says assume it's a clockwise direction. Negative over here, it means what? It means the opposite direction. So magnetic field through the solenoid at some over this stretch of time, magnetic field will be that way. Over this stretch of time, magnetic field will be in the opposite direction. But we will need to answer. We will need to find only the value of the current at a certain moments of time. So we're not going to look at the direction. All right. Okay, and again, which current do we have to find? Current in the loop. So what needs to be found? Find I induced, and emphasize loop, in the loop. Here, and let me show probably. All right, so over here. So that is the current in the solenoid, and we need to find the current in the loop. And let me draw magnetic field lines. So that's basically B external for the loop. Right? Okay, so that's the situation. And again, the idea is external magnetic field is created by the solenoid and the loop is exposed to that magnetic field. Okay, let me write so this word. So B external is created by the solenoid and the loop is exposed to this B external. So pretty much physics is over here. Okay, that we need to apply Faraday's law. Okay, and now, again, flux, and shoved it into the Faraday's law, right? But first, let's do step by step. Expression for the magnetic field, quiz number 5, right? B external. It's you remember, mu naught n small times I. N small, again, quiz number 5, you should remember, it's a number of loops per unit length. Number of loops in the solenoid. Number of loops is given, the length is given. So n divided by L, that's n small. Mu naught n divided by L times I. Since I knew we're going to use this expression a lot, that's why I asked you to derive in your homework this formula, right? So it should be still fresh in your head. Okay, so that's what we need for flux. Now let's find the flux. Magnetic flux, and of course, let me emphasize through the loop. Again, it will be B external times area. Okay, let me write of the loop. Again, dot product area of the loop, I can align it either this way or that way. I will align area vector this direction. This will be my A of the loop, right? In the same direction as the external magnetic field. So to make angle 0, right? So theta equals to 0 degrees. Right. And again, external magnetic field exists only in this part. Right? Over here, this magnetic field is 0 outside of the solenoid. Over here also there is no magnetic field. So this dot product gives us what? B external times area of the solenoid. Right? Area of the solenoid. Right? So only that part of the loop, which is area, which is equal to the area of the solenoid, is exposed to the magnetic field, right? So again, like that's what we have here. Here we had this shaded area was exposed to the magnetic field, and now only this part of the loop is exposed to the external magnetic field, and that part of the loop, area of that part, equals to the area of the solenoid. Okay, so now this is circle cross-sectional area, so we can write, how should I write it? Yeah, pi r solenoid squared, area of the solenoid, right? N times B external. Should I plug it now? Yeah, why not? All right, so now B external goes over here, and let me show that. And as a result, we will have pi, okay, blended too much, pi r solenoid squared times mu naught n I divided by L. So that's the flux. That's the expression for the magnetic flux through the loop. And now, shoved into the Faraday's law to see. Okay, I will probably write it here. So EMF equals the problem says find the magnitude of the current. So I'm going to put the sign of an absolute value, right? Direction, the problem doesn't ask about the direction because that will be additional step, require additional steps. So d phi of the loop over dt, right? And let's see which parameters are constant in time. Okay, maybe I will write first d over dt pi r solenoid squared mu naught n I divided by L. I just rewrote it, equals. Carefully, pi is constant outside. We can take it outside. Radius of the solenoid, constant, also outside. Mu, universal constant, also can be taken outside. Number of loops, constant, outside. L, length of the solenoid, outside. Current, you see what happens to the current? It changes. So current must stay under the sign of differentiation. So I can write, so EMF equals to, okay, all those constants, pi r solenoid squared mu naught n divided by L, and rate of change of the current. So that's expression for EMF. And now we need to get the current I induced. Of course, it will be EMF divided by resistance, right? So it pretty much I just rewrite all that with resistance in the denominator. So it will be pi r solenoid squared mu naught times n divided by L times R, and rate of change of the current. Okay, so this, okay, let me frame it because it's basically like a formula which we derived for this particular case, for this problem. And now the problem asks, we need to find the value of the current at these points. 0.5 seconds, 1.5 seconds, and I think at 2.5 seconds. So basically you just need to apply these 3 times. Can you tell me what will be the value of the current at 0.5 seconds? What happens to the current at that point? It's constant. Of course, the value of the current is 20 amps, but it doesn't change in time, and that's what we have here. Current doesn't change in time. So di over dt is 0, and the whole current in 0.5 seconds will be 0. Similar story, or I can say exactly the same story, is at 2.5 seconds. Okay, let me hold you for a second. Let me part A, right? So I at 0.5 seconds, right? So equals to 20 amps. But di over dt at 0.5 seconds equals to 0. And let me show that pretty much that's what you need to use over here. And as a result, I induced at 0.5 seconds equals to 0. And as I said, at 2.5 seconds, it's the same story, right? Part B, current at 1.5 seconds. The value of the current, okay guys, the value of the current is 0. But what we don't need the value of the current. We need to know how fast current changes in time. We need to know the slope. di over dt, it's a slope of this graph. Here slope 0, here slope 0, here slope is not 0. You should be able to calculate that slope, right? So although value of the current is 0 amps, but di over dt at 1.5 seconds is not equals to 0. So you will calculate it at home, and at this point we can call it a day, pretty much. So now it's clear what needs to be done. So finding the slope at this point, anyone can do that, right? This point is given 20 minus 20, this point is 20. The distance is what, 1 second? So time distance, right? Okay, so this problem is a little bit more challenging, right? And I don't remember if I assigned this problem as a homework, but anyway, I will send you my solutions, right, to this problem. But from this, after this point, you should be able to handle it by yourself easily, right? Although philosophy is exactly the same still. We have a loop, but now only small part of the loop is exposed to the external magnetic field produced by the solenoid. Okay guys, thank you. Sorry for holding you a little bit longer.